Okay. All right. Good evening, everybody. Welcome to Professor Paul Hellier's inaugural lecture. My name is Professor Manish Tiwari. I'm Director of Research in Mechanical Engineering Department. And I have the honor to introduce our most esteemed colleague who actually works on things that may save the planet. And that's why we see a number of next generation students in the audience as well, which we are very happy about. So welcome to all of you. So Paul is Professor of Sustainable Energy Engineering. I'm reading because I'm terrified of making mistakes. Paul's achievements are numerous. I have tried to summarize it a little bit. Okay, so you're going to have to bear with me. He is Professor of Sustainable Energy Engineering in Department of Mechanical Engineering in UCL. Paul is an environmental engineer. His first degree is environmental engineering, from what I reckon. So this gives you an impression that we take all sorts on mechanical engineering and we care about environment ourselves too. Since completing his PhD in UCL, he's focused on molecular structure of future fuels, and he has worked in particular with partners from across industry, academia, and public authorities in development of sustainable net zero fuels with organizations involved in waste valorization. It means taking waste and converting it into useful things for kids in the room. You can do that, and he'll tell us about it in one moment. And fuel production, emission control, and assessment of health impact of combustion, which is how most of our energy, even to this day, is produced. So it's important stuff. Paul's research group and experimental facilities focus on development of novel renewable fuels across transport sectors, going across road, going across marine, as well as aviation. Please come on in. It's okay, there's plenty of seats at the front. There's a very friendly audience here. We should be fine to get across. And he's worked on bio-derived and synthetic fuels such as hydrogen and ammonia as well as investigating practical engines. I think of Paul as one of those unique individuals who's equally comfortable thinking about molecules as well as proper engineering stuff, which happens at much larger scale in mechanical engineering. So with that, I'll hand over to Paul, but before I do that, a few housekeeping items so we don't forget. There is no fire alarm or drill setup. So if we hear alarms, we should walk. There will be plenty of people following around, so we should just walk down and go out. I hope that will not happen, despite Paul's best efforts, and you will see what I mean in a moment. Second, after we finish this, there is drinks and nibbles downstairs as well, and I definitely suggest that we walk downstairs after that. And I'll give Paul about an hour. He will get a feel. He's an amazing lecturer, as you will see. I've had the pleasure of teaching with Paul. I hope you will enjoy it just as much as I do. Welcome, Professor Paul Hellier.
So thank you, Manish, for that very, very kind introduction. I'm very honored to have such a kind introduction. But what I'm most honored by, what I'm most excited by tonight is that you're all here. So thank you so much for coming out this afternoon to hear me talk about the kinds of things that I'm lucky enough to get to do all the time. So as Manish was saying, I work with fuels. I work with fuels all the time, different types of fuels. But before we start talking a lot about different fuels, who today has interacted with a fuel? Who's come face to face or hand to hand? Yes, at the back there. Please tell us, guys. You have an advantage, which I'm very glad you're expressing. But what fuels have you interacted with today?
I've interacted with gasoline, sometimes diesel, sometimes ammonia, a bit of everything really.
Excellent, good. Now you're a researcher here. Not everybody gets such a feel for different fuels. Anybody who doesn't have the privilege of touching those fuels firsthand in their day-to-day pursuits come, into contact with some fuels today. Anybody? No? Oh, well, let's see. Who walked here today? Very good. I'm very pleased with the people who walked here. Who cycled here today? Excellent. I'm even more pleased with the people who cycled here. Well done. But who took some kind of conveyance that relied on? Yes, yes. Lots of people, lots of people. And so you may not have come into physical contact with those fuels, but you've certainly experienced the power of those fuels. You have the privilege of releasing that chemical energy that's inside of those fuels and utilizing it to get you somewhere. And so there are fuels everywhere. We all come into contact with fuels. And when we talk about fuels, all we're really getting at is that these are a way of storing energy, turning it somehow into a useful chemical perhaps, and then conveying it and then releasing it at the right time and getting it to do something useful for us. And so that's what we're going to talk about tonight. But first of all, I thought I would, because I'm very lucky, I know many of you here today, but I also wanted to take this opportunity to introduce myself a little bit. So, as Manish very kindly said, I didn't start out as a mechanical engineer, and it's very kind of him to explain that we take all kinds here, because we certainly do. But I started out studying environmental engineering at Cardiff University in Wales, so quite far from London. And yeah, can anybody help me identify, where am I in these photos? For example, this photo over there. Yes, where am I? I'm at a farm. Yes, good answer. Good answer. And is this me? No, I was not a sheep. Oh well. No. So I studied environmental engineering. And that meant kind of thinking quite holistically, quite big sometimes. So what I was doing, other than obviously enjoying the presence of some sheep over here, is that I was thinking about the environmental impacts that could arise from a proposed engineering solution. And while I was studying environmental engineering, I was doing other important things. I was learning to stand in particular ways. And what I was really gaining an appreciation of was the fact that as engineers, we can do all kinds of things. We can do lots of different things. But what's really difficult and really challenging is knowing what's the right thing to do. What's the best way to solve some problems. And so I got really into compost when I was studying environmental engineering. I had a whole project in one of my final years that was all about compost. And what got me excited about compost was the fact that we were taking one problem. We were taking this problem of how to divert waste from landfill, how to deal with all this municipal waste, and we were building some kind of huge composting facility. Sadly, it was theoretical, but we were building some kind of huge composting facility. We were thinking about what went into the compost in order to get the best things out, in order to try and take one problem, this problem of getting rid of all this waste, and then solving another problem, how to generate some renewable energy from all that waste material. And so I really enjoyed my time as an environmental engineer, and I developed this kind of appreciation. But the world was different back then. Who here remembers the mid-noughties? Yeah, I think more people than are putting their hands up. But anyway, it was a great time. There were many great things. And in the UK, we were blessed with two men who were in charge. And two of those men were Tony Blair, and I'm going to try really hard not to address what he said about net zero recently, because this is being filmed. But also, he was joined by the Iron Chancellor of the Clunking Fist fame. Now, this man had a passion for a certain type of fuel and a certain type of combustion engine. Does anybody know which type of fuel and combustion engine the Clunking Fist was so pro? Yes, sorry, what was that? Diesel, yes, exactly. And why did he promote the use of diesel? That's fair. Anybody who cares to remember why diesel was being promoted as the fuel of choice in the mid-noughties? He considered it was linked to sustainability, perhaps a certain type of sustainability.
Air quality.
Oh, it wasn't linked to air quality at the time, but it had an inadvertent ramification on air quality that we'll come back to. Money, yes, yes, it was a financial concern. Gordon Brown wanted to incentivize the use of diesel vehicles, not because he thought it was more sustainable necessarily, but because he thought it would save people money. And so he incentivized that. He made it so that the duty on these kinds of vehicles was lower, so that people would actively switch to a diesel vehicle. But the very thing about diesel combustion, which means that it can be more fuel efficient than other types of combustion, spark ignition combustion, also means that it's much harder to control the pollutant emissions. It's much harder to control things like the particulate matter and the nitrogen oxides that are produced. But he didn't know that at the time. So shall we let him off? No! Let's not let Gordon Brown off so easy. Anyway, at the same time, when I was studying environmental engineering, it was good. I was gaining an appreciation of why we needed to address these concerns, why we needed to reduce CO2 emissions. But in retrospect, what was really concerning was this whole concept up there, this whole idea of peak oil. Now, for those of you who don't remember the noughties, what's peak oil? Anybody? Yes. It is the idea that there'll be lots of oil at one point, and then what happens? And then it decreases. Yeah, the amount of oil available decreased. And so in retrospect, what was really disturbing is that in the mid-noughties, one of the major motivations we had for trying to diversify our energy, to think about renewable energy generation, was the fact that we weren't so worried about climate change. People were accepting of climate change and the need to be worried about it. But actually, a major motivation that lots of people were pushing was the idea, well, actually, this oil is going to run out at some point. That's what this plot shows. It shows the decades along the x-axis, and then on the y-axis, it has the billions of barrels of oil per year being produced. And what it implies is that at some point, it was going to run out, and there wouldn't be any more oil left. And so what was really disturbing is that was the major motivation for trying to diversify. The fact that actually we wanted to maintain a certain lifestyle, a certain quality of life, and to do that we had to find something different to use as our energy before the oil ran out. And we don't teach that anymore, and I'm really, really glad of that. Anyway, against this backdrop, I had to figure out what to do next after my environmental degree. And what I really wanted to do was to carry on learning things, to carry on trying to solve those problems, to be creative as a scientist. Now, can anybody guess where this is? Some of you, yes! This is my lab, correct. Very good answer. So this is where I was lucky enough to come and do my PhD. I was very fortunate. I met for the first time my supervisor, Professor Nikos Lalamatos, and I came here and I was given the keys to this room. And it fast became, and still is, my favorite place in UCL. It's 2 floors underground right now. If we had time, we'd all be in there for a tour. But anyway, what was so fantastic about this lab is in there I had the opportunity to test things, to experiment, to do all kinds of burning type experiments within reason. And it was amazing. I was given complete freedom to explore and understand how when we change the molecular structure of a fuel, what that did to the combustion characteristics, what that did to the emissions. And as you can see, it made me really happy. And a big part of what made me really happy and enabled this research work was this device here. Now, can anybody, I can see a few people in this room who've had the pleasure of interacting with this room, with that device, but I have some people with their hands up at the front. What is that? Guys? Oh, actually, that's sat on top of, in this particular photo, that's only a small diesel engine. I've got a bigger one now. But, yeah. But what's the device? Okay, so the device is a special fuel system that we developed. And I can't take credit for this. This was inspired by my direct predecessor and the person who actually passed me these keys in person, Dr. Alessandro Schomborn, who is now at the World Maritime University in Malmö, Sweden. And he inspired me to create this device in the first part of my PhD. And what it was basically a way, and I'm not going to go into the technical details of how it worked, but it was a great big high pressure pump, which meant that we could test anything we liked as a fuel. We had very few limitations. It didn't need to be a fuel. It could be a chemical, it could be solid. I spent lots of time with a hairdryer at one point. It was great. And this is how it looked on top of one of our light-duty diesel engines. And what it enabled was this understanding, this appreciation of how when fuel molecules change, on the basis of a single atom perhaps, what that does to the resulting way in which the energy is released. And sorry, I'm just going to take a quick sip of water from my green bottle. It's not fuel, no. There it could have been. And yes, so what this device enabled was us to study on a molecular level how these fuels behaved, so that as we hopefully, all the time with this motivation to diversify away from the fossil fuels, to redesign, to reimagine fuels, we can understand how tiny, tiny changes to the fuel molecular structure might impact on the way that the energy was released and the emissions that were produced. And this is one of the studies we did. And I'm going to show you a few more plots like this. So I'm going to explain what it means. So on the left-hand side, we have the in-cylinder pressure measured inside a diesel engine. And this is happening very, very quickly. So imagine this is only half a piston because I thought it was enough. But half a piston, this is what's inside that engine. And it's moving very, very rapidly. Maybe 20 times a second. It goes up and down in its stroke. And when it does that, the first thing that it does, before any fuel even arrives inside the combustion chamber, is when it moves up, it makes the in-cylinder volume, the amount of trapped air inside the combustion chamber, it forces that to be in a smaller volume. It forces it to be at a higher pressure. And that's ideal. Because when it gets to that higher pressure here, just due to compression, what's not shown here, but what's actually the case, is it's also very, very hot inside the combustion chamber. And because it's such a high temperature, it means when we inject a fuel, the chemistry takes over, there's an elegant process of auto-ignition, and the fuel ignites by itself. And so what we see here is the in-cylinder pressure on the y-axis, and then along the x-axis, this is crank angle degree. This tells us where the piston is. And the important place is 360 crank angle degrees. That's when the piston is at the top of its stroke, and there's only a very, very small space left for the fuel to start burning and release its energy and then drive the piston back down, creating power out from the engine. And so we can see here different fuels creating different amounts of pressure to drive the piston back down. And what we can do, because we know what the volume is over time, we can go away from looking at pressure to looking at what we have here instead, which is the heat release rate. So this just tells us how quickly is the fuel burning and releasing energy. And what we could see is that there are lots of differences that occur due to these different fuel structures. Now, who here is a chemist or has a passion for chemistry? Yes, yes, good. Can you tell me, what are all of these? They're molecular structures, yeah. But what kind of, they're all something else. Yeah? They're all hydrocarbons, correct. They're all isomers, excellent, they're all isomers. Now tell us, what's an isomer? Yeah. So that's a good way of describing it. These isomers, they all have the same constituent components. So every one of these molecular structures up here is something called an octene. So it means it has 8 carbon atoms, but not quite enough hydrogen, which means that you always have a carbon-to-carbon double bond, which is significant in terms of combustion and the production of things like particulates. But these all have exactly the same number of hydrogen and carbon atoms, but they're arranged slightly differently. They're arranged slightly differently so that double bond is in a different position. It's either in the 1 position, or the 2 position, or in the 3 position, or the angle is completely different. So these are all pure chemicals. We had to get them synthesized. We had only tiny amounts that we were able to test in the engine using the ultra-low volume fuel system. And what we saw is that even though these are very, very tiny differences, it still had a significant impact. So this was one of the first things we did, but it hinted then at the potential of thinking about fuel design on this molecular basis. Sorry guys, I need another drink. So, what? Oh, it's not my water. Oh, thanks guys. I was going to drink that. Oh, well, why shouldn't I drink this? I might get sick. I might do. I don't know. It looks all right, doesn't it? It's tempting. Your cut drink's the same colour. But...
It's just a water bottle.
Oh, fair. Okay. Well, I'm going to take the advice. I'm not going to drink this. But why? Why not? What's actually inside of here? Yeah? It's not oil. It's not oil, but it's something that contains oil. Yeah? It's not, well, I hope not. I really hope not. Yeah? Yes? It's algae! Good guess. Oh, well, it's an excellent guess. This is the microalgae. That's why it's such a beautiful, lovely green color. And microalgae is fantastic because algae is a single-cell organism. And what it does is it grows and it multiplies and it stores energy just by growing off of sunlight, by undergoing photosynthesis, and by breathing in carbon dioxide. And as it does this, oh, what am I just the wrong slide. I was going to ask you guys something else. All right, guys. Who lives in Camden? Oh, yes. Yeah, you live in Camden. Okay, good. Anybody else? You used to live in Camden. Okay, all right. We'll come back to the algae in a second because, yeah, Camden, it's not all good news. It's lovely, but this is a report from what used to be Public Health England or the UK Health Security Agency. And so what they identified is they went borough to borough and they were looking at the effect then of how different pollutants were impacting people's health. And this is really disturbing because what they found, and UCL's actually down here in Camden, it's not up there, and what they found actually is that just living in Camden and being exposed to the kind of air quality that's here is having a real impact on people's health, and it's resulting in premature mortality, and it's resulting as well in people losing years of their lives. So I'm really sorry guys, because that bit was really serious, and this bit was meant to be funny. So that's not very good. Anyway, back to the algae. The algae is, this is my algae. How much algae do I have in here, guys, by the way? Yeah. 100 grams. We have 100 grams at the front. Anybody higher or lower than 100 grams? Higher. Excellent. We have higher. Anybody else? Lower. How much lower? 2 grams. Okay, do we have any advances on 2 grams? Half a litre. So there is about nearly 900 milliliters of green algal stuff. But I suppose my question, to be more specific, is what is the mass of algae that's inside this bottle? So we had 2 grams and we had 100 grams. Do we have anything else? Come on down to the front. There's loads of space, please. Yeah. Yes. 300 grams. No, we're going to go lower than 300 grams. Yes. 0.5 grams is pretty close. And so 0.5 grams is not very much. And this algae is great. This is what an individual algae cell looks like. And what it does is just like us, when it eats too much and it needs to store energy, it stores oils, it gets fat, effectively. But if we want to get to that oil and we want to use it as an energy vector to make a biofuel, Can anybody think, what's the problem if actually I've only got about half a gram in my bottle of algae? What challenge are we facing? Yes? It'll be hard to get, and why is that? Yes? Yeah, it's always difficult to get that little bit, isn't it? Yeah, but why specifically? Yes, yes, yes. Yeah. So to get a reasonable amount of energy, we have to harvest a lot of it. That's true. Yeah, exactly. So I think we've covered it really, because if we think about what we want the energy inside there for, we want it to be renewable energy that we can use to offset the use of fossil fuels. But to do that, if we have to invest lots of energy in order to take away the water and get to what's inside the cell, then that's not very productive. And so I was really lucky though. So during my PhD, I got to meet a molecular structural biologist, Professor Saul Purton, and Dr. Lamia Al-Hajj, and we got to work together on genetically modifying some microalgae in order to make it better, to make it easier to get those fuels. So those fuels, rather than being stored inside, would be excreted into the water. Now, I'm actually going to drink some actual water now. Right. So, yeah, we got talking about different fuel molecules. That would be good because they had some ideas about what the algae can make. So this kind of map behind me, this is what the algae would make in its metabolic pathways. It would start at the top there, and then what the structural molecular biologists could do is they could introduce these additional red arrows in order to produce or to divert the metabolic pathways to make something slightly different. And sorry, just a second. And what they could do, for example, is produce this molecule in green here. Now, I guarantee that many of you have met this molecule before. And to prove it, I'm going to ask somebody to sniff my algae. Who wants to sniff my algae? Okay, sniff my algae. Sniff my algae. Anybody? It's familiar. Hold that thought. Yeah. Anybody else want to smell my algae? Yeah, smell my algae. You like it? You like it? Yes, smell my algae. It smells citrusy, doesn't it? Yeah. Who else wants to smell my algae? Yes. Yeah, you enjoying it? Oh, I'll say yes, please. Yes. Yeah. It's good, right? Yeah, it's good. Who else wants? Oh, thank you, thanks. Yeah, we're going all the way back now, I think. Yeah. Oh, please smell my algae. Who else wants to smell my? Yeah, I've got lots of takers. Sorry, this is going to take a while. Okay, thanks. How's that smell? Nice. You like? Yeah. Okay. Yeah. Okay. Okay. So we have to hand it back to Mitchell there, who's insisting that he gets to smell the algae. Sorry, could we pass it to Mitchell? Okay. Thanks, guys. So for those of you who've had a whiff, did you like it? Yeah. Oh, not sure if you liked it. Well, it won't come as any great surprise to hear that I like it. But thanks, Peter. Okay, brilliant. So that's it, right? Yeah. You want to? Okay. Sorry, can we pass it along, please? Thank you. Okay. Yeah. So, any guesses? Where might you have smelt that before? Citronella. It has got a citronella kind of vibe, hasn't it? And some of those names are a bit of a giveaway. But I'm starting to look at people a bit more closely now, because some of you may have met this very molecule this morning already, or any other time during the day. I don't know. It's not up to me to judge. So, where do you think you might have met this particular molecule already today? Sorry? In a bakery. It's an interesting bakery. I've not been there. Okay, that's interesting. Something else. A cleaning product. All right, I'm going to be really horrible and pick on somebody. And I'm going to give you all a clue because he's looking at his phone right now. Errol probably didn't meet this morning. Did that help? Does that give you guys a clue? Go on. Yeah. Sorry? Have a think. Anybody else? Yes. Sorry? Say that again. Oh, like a fragrance. Yeah, a particular kind of fragrance. Yeah. Yes. On a river? No, I hope not. I think that river's not very healthy if that's the case. Shampoo! Excellent answer. Yeah. Amazing. So yes, you can all go home later, and if you check the bottle of shampoo that you presumably own, then you can find halfway down the ingredients list this molecule, geraniol. So, in summary, it is an excellent smelling fuel. Sadly, it's not a very good burning fuel. But that's okay, because we knew why that was. What we could do is we could straight away have a look at this, and we could say, well, actually, your problem is quite simple. You've got too many double bonds, you've got too much branching, and you've got an alcohol group. But it was okay, because the structural molecular biologist said, well, that's all right. What we'll do is we'll come up with a whole range of different molecules, and you can burn them in your engine. So what this plot is showing us now is also very interesting, because this is all those different molecules that can come about via the metabolic engineering of the algae on the x-axis, and then on the y-axis is the ignition delay. So the ignition delay is that time, that interval, where all of this very elegant auto-ignition chemistry takes place. And during the ignition delay period, that's the time in between the fuel finding itself in its high pressure, high temperature environment inside the diesel engine, and then the point at which it starts burning and releasing energy. That's the ignition delay, and it's really important. And it's similar to those of you who've heard about it, it's similar to the cetane number. Because if that ignition delay period takes too long, then we don't get the fuel burning at the right time and releasing energy in an efficient manner. And it also has a big impact on things like the emissions of NOx, nitrogen oxides. And so what we could see, though, when we tested all these different fuel molecules, is that the biggest, the most significant impact we could arrive at was when we did one tiny, tiny change to the fuel structure. And we went from the geraniol, the shampoo ingredient at the top, down here to geraniol. And all that we'd done, all that we changed, is we'd gone from having that alcohol functional group at the end to having the ketone. And what we can see when we compare the geraniol over here to the geraniol down here is that's what had the most significant impact in helping to reduce that duration of ignition delay and make it a more useful fuel. And it also smelled really good still. So. The world, though, was changing, and in a good way, until recently, perhaps. And so in the mid-teens, we had the Paris Agreement. And this was really important because this was one of the first times that internationally different countries had come together and they had agreed to try and limit the temperature rises that we were seeing globally due to global warming, due to that release of CO2 from fossil fuels. And what they'd come together and agreed was that they wanted really hard to try and get to this limit, to stop temperatures from rising greater than 1.5 degrees from where they were pre-industrially. And so there was a lot of interest, there was a lot of sort of momentum and goodwill towards doing this, and there was a lot of understanding as well that this was really, really important. And that what this plot is showing here, and I borrowed this plot from the Intergovernmental Panel on Climate Change, is that every additional ton of CO2 that gets released into the atmosphere, every additional ton of CO2 is going to result in a greater and greater increase in temperature relative to those pre-industrial levels. So there was understanding, kind of mainstream understanding, the idea of peak oil was going away, and instead there was understanding that actually those fossil fuels, that oil had to be left in the ground. And what was so important was that we try really hard to limit those temperatures. And so that meant that we were being much more creative, much more open to the use of different renewable fuels. For example, fuels from waste. So does anybody know, in the UK and in Europe, what is the most commonly used biofuel at the moment for a diesel engine? Any guesses? Yes? Oh, hydrotreated vegetable oil, or HVO, is very popular. But I'm thinking of something that you don't have to go out and buy especially. I'm thinking of something which is just present, it's blended into any kind of diesel that you buy at the pump? Any guesses? Biodiesel, exactly. What's a biodiesel? It's a fatty acid. Oh, go on then. That's a really good answer, sorry. So it's a diesel that's not produced from fossil fuels. It's a biodiesel. It comes from biological origin. So it could come from plants or it could come from animals. And what it is specifically, though, what we really mean when we talk about biodiesel is fatty acid methyl esters. And so in the UK right now, those fatty acid methyl esters, which are blended into the pump diesel that we can go out and buy right now if we want, and we can buy something called B7, which means it has 7% of those fatty acid methyl esters blended in. What is the source of those oils? What do you think is the ultimate source of those oils in the UK at the moment? Where are those oils that get used to make biodiesel? Where do they come from? Food waste. Yeah, that's an excellent answer. What kind of food waste? Yeah, so mostly like plant oils. Yeah, mostly plant oils. So like used cooking oil. Yeah, I would agree. That's where it's all coming from. But there is a problem. The problem being that we don't consume enough fried chicken. And therefore, there isn't enough of this used cooking oil. So we need to diversify. We need to think about other sources of waste cooking oil. And can anybody think of another source of a waste oil? Yes? Oh, go on then. That is an excellent question. Why specifically fried chicken? That's a really important question. And actually, it doesn't specifically have to be fried chicken. It can be any kind of waste oil. But I know, based on the number of Sam's chicken cottage I see on my way home, that fried chicken is a good option for us. But that's a good question. Good. Any other kinds of oils we could use, though? Oh, yeah? Baking oil? Yeah, we could use waste margarines and butters if we had enough. That's a really good idea. Yeah. Okay. Anybody else want to mention anything else we could use? Go on then. Coffee. Yeah. So coffee. Coffee is an excellent source of oil. So I like drinking coffee, even my pretend cup of coffee. That's not fooling anybody. But also, we can make a fuel from coffee. So these are some oils produced from coffee. I'm not going to let you sniff these because they don't smell so good. But you can have a look. You can certainly have a look. Yeah, you can see how it's all viscous and brown like coffee. Yeah? Yeah, it's the same color as something like vinegar. Who else wants to look at some coffee oil? I've got, yeah. Just appreciate its viscosity. So this is a fairly normal looking oil. And that's okay. It's a good oil. It works well. And so we did quite a lot of work making these fuels from coffee. And it was good. It worked. So I like drinking coffee. I'm sure lots of you like drinking coffee. And as you can see, the engine enjoyed drinking coffee as well. That's some of this coffee oil up there in the fuel funnel being consumed. And this is another one of those heat release rate diagrams. And the whole point here is that basically the way that the engine performed while it was working with the coffee oil was exactly the same as it was with the other biodiesels, the soybean biodiesel and also the rapeseed biodiesel. And that's okay, because when we look at the chemical composition of these oils from coffee, they're very similar to these other fuels as well. And we can understand things like the impact on the emission of nitrogen oxides based on things like the degree of unsaturation that we mentioned earlier as being important of these coffee oils. But there's a problem. What's the problem? Sorry? Why is it so expensive? It's produced from coffee waste. Because I can have my cup of coffee and I don't eat, well, I have eaten coffee grounds. I don't do it regularly. And so what's left over are these spent coffee grounds. But what's the problem with these spent coffee grounds, these waste coffee grounds? Sorry? There is less heat. Yeah, there's a little bit less. Okay, so let's clarify what's going on here. There are two things going on here. There's the SCG oil, the spent coffee ground oil, and that is the more viscous of these samples, which has not undergone transesterification, thus reacting it with an alcohol to make it less viscous. And so because that doesn't mix so well with the air after the fuel is injected, this initial part of combustion, the premix burn fraction, is smaller. But if you look at the SCG B100, which is the biodiesel version of the coffee oil, that has been transesterified, reacted with methanol, so it has a lower viscosity. And so that mixed much more readily with the air, and it produced a more similar heat release profile to the others. So that's okay. That's not such a big problem. I'm more thinking about how we make, yeah.
Is it like the logistics of collecting the coffee grounds?
Yeah, I mean, that's challenging, but we were really lucky. We were partnering with a company who had a plan. They came from UCL. They were architecture students originally, and they wanted to go out and make a business model of all that. And did I see a hand up back there? It is too wet. It is too wet originally. That's the challenge, because just like the algae, it's not as bad as the algae in terms of the amount of water that comes with it. But after you make your cup of coffee, what you have left is spent coffee grounds, and about 60% of that is still water. And that's a challenge, because even though getting the oils out of those coffee grounds is actually quite a lot like making an espresso, you can do it under high pressure and high temperature to help drive the oils out of the coffee grounds. Even though you can do that, that process is inhibited. So we did a lot of work understanding what was going on. In fact, it was my first PhD student, Dr. Yanis Apimilopoulos, who's here tonight. He did a lot of work. This is all his work in the lab, understanding what was the effect of sequentially trying to get the water out of those coffee grounds in order to make the process more efficient. And what we found is that in order to get this yield of coffee back up to where it needed to be, in order to make the process efficient, is you had to dry off lots and lots of water. And that was expensive again. It was also not a good business model. Who can guess what else were we losing when we were heating up these wet coffee grounds and getting rid of the water? Yes? We were investing energy, yeah, which we don't want to do when we're trying to get renewable energy out. Yeah, that's a good idea. Anything else? What were we losing as we were heating up these coffee grounds? Sorry? We were losing water. And yeah, but what went with the water? Any guesses? Yes? It could have been things that contained oxygen. Yeah? What do I like about coffee? Is it its lovely brown appearance and the fact that it's normally hot while I drink it? What do I like? I like caffeine from my coffee, don't I? Yeah, I like the way it smells. I do like the caffeine. But yeah, I like the way it smells. And yeah, basically, when you dry your waste coffee grounds, you lose lots of those aromatic, those volatile species. And those actually have an intrinsically much, much higher value to be sold onwards into the coffee industry than the coffee fuel itself. So it was exciting to look at, but we're not yet all driving around with coffee biodiesel. But things are getting better in some respects, because we've gone from mostly thinking about biofuels in the context of road transport and thinking about how to decarbonize road vehicles to thinking about, well, maybe we can electrify, and that's a really good solution for lots of those passenger vehicles, lots of kinds of journeys, and thinking about different sectors, like Manish said at the beginning, thinking about shipping, thinking about aviation as well. And that's starting to change. And sectors like the marine world, the shipping world, have gone from not really being too invested in the idea of renewable energy or biofuels maybe 6 or 7 years ago, to now setting really, really ambitious targets. And when they do that, that opens up new possibilities to think about fuels that have literally zero carbon in. And so one way that we can reduce the emissions of carbon dioxide to atmosphere from fuels is by using biofuels, fuels that are renewable and have less of that fossil energy invested in them. Another way is that we can literally take the carbon out. So, what is this molecule up here? Any guesses? Yeah? Was that a hand?
Yeah, ammonia.
It's ammonia, exactly. And so I'll just get my vial of ammonia. I don't really have a vial of ammonia. Who do you think I am? Why don't I have a vial of ammonia? Go on. Yeah, it's really toxic. If we smell it, it could well kill us. And also, who knows what ammonia smells like? Go on then. Wee-wee! Oh dear. Leaving the idea of it. It doesn't smell great, guys. And it is also, all joking aside, really, really toxic. But when we think about different ways of ammonia, and we think about something like shipping, the marine world, where compared to road transport, actually we're much less constricted in terms of the amount of space we have to store our fuels, that opens up new possibilities. So this down here is ammonia in a different form. This is ammonia, aqueous ammonia. That means it's ammonia inside water. And this is some work pioneered by Dr. James Frost, who's also with us here tonight. And what we did is we wanted to see if we could inject this aqueous ammonia, this ammonia in water, so it didn't smell as bad, and it wasn't as dangerous because it was in water the whole time. If we could inject that into our engine and still get some useful work out. And we did. That's what this, another heat release, I'm afraid, that's what it shows. It shows that as we added up to 25% ammonia, or aqueous ammonia, into the engine, we were still getting useful work out. So we were displacing energy that was coming from burning, reacting oxygen with carbon, with instead that from burning with the hydrogen that was coming off of the ammonia. Now, ammonia uses that nitrogen then to carry the hydrogen. There's a conveyance of hydrogen to get it into the combustion chamber in perhaps a slightly more convenient manner. But, can anybody foresee any problems with adding extra nitrogen into the combustion chamber? NOx. Excellent, excellent. How is NOx made? Oh, you didn't say NOx. Who said NOx? Oh, good. Okay, how is NOx made?
During like a high temperature zone inside the engine.
Yeah, exactly. So, right now in this room, we have the ingredients for making loads of nitrogen oxides. Any guesses? What are those ingredients? Yes?
Like some type of oil.
It could be. Yeah, we could burn some of the props I brought and we could make some NOx. But also, the reason we could do is because we've got lots of nitrogen and oxygen. And the way that nitrogen oxides are made during combustion is that they make use of the nitrogen and the oxygen that are already in the air. And what happens is you get sufficiently high temperatures that these two chemicals, which are here right now, and most of the time aren't reacting, they start reacting and they start combining and forming these nitrogen oxides, NO and NO2 and N2O in some cases. But what do you think might happen when we also put nitrogen in our fuel? Yes? No, it makes it combust slower, actually. Yeah. But good guess. Anybody else? What's the effect of that? What's the possibility we're opening up now that there's nitrogen in the fuel?
N2O.
We could make N2O. Good, exactly. We're opening up new ways of making nitrogen oxides using the nitrogen. It's already connected to the hydrogen and getting involved in those chemical reactions. But what did we see then in the engine exhaust? Well, what we saw, in fact, and this is the plot to concentrate on, is as the amount of ammonia increases along the x-axis, the amount of nitrogen oxides that we measured in the engine exhaust, initially it increased because we were getting more power out, we were introducing more of this ammonia with nitrogen in, opening up new ways of making nitrogen oxides, but then actually it started to decrease as we went to higher and higher levels. And that's because of the water being present inside the combustion chamber as well. The ammonia bringing along all that water as well, it counteracted this effect of more fuel-bound nitrogen, and it helped to lower temperatures and mean that actually the amount of NOx being produced eventually decreased. But any guesses? Why did we only get to 25%? What happened afterwards? Yes? The NOx did disappear. Yeah. Any ideas why, anybody? Because it doesn't burn anymore. Excellent. So, the water drives down temperatures and it makes it more and more unstable. So, we saw that actually the need to reach net zero, the need to decarbonize has become more and more important. It's become more prevalent in the minds of the public, in policymakers, and increasingly the same is true of air quality as well. And we can see here the ULEZ being expanded a few years ago, and it wasn't popular and it was politicized, and that was really sad because at the end of the day it was a public health measure, and it needs to be a public health measure. So another part of what we do is we look not just at the exhaust emissions in terms of the mass and the number of particles that are being produced during combustion and then are emitted to atmosphere, but we also try and understand how dangerous those particles are, because that's not regulated at the moment. And the reason why some of those particles are so dangerous is because of how far they can get down into our lungs. They can get right down. The smallest particles can make it right down into the bottom of our lungs. And when they're there, what they can do is they can convey this kind of material up here into our bloodstream. They can have carcinogenic effects on our bodies. And the effects that they have vary drastically because we get different kinds of chemical compounds that start off from coming from the fuels but have a different level of toxicity associated with them, depending, and going back to the idea of isomers and molecular structure, depending on the exact structure. These are called polycyclic aromatic hydrocarbons, and depending on these minor differences in the structure, the impact that they can have on our health massively varies. And so that's something that we wanted to look at as well. And so we can produce soot from our diesel engines, and we can use current fuels as well. And what we do is we work in collaboration with the UK Health Security Agency, with Dr. Martin Leonard, who is a principal toxicologist there. And what we've been doing is generating soot from our test engines and generating that soot from different fuels and then doing two different things with the soot after we've collected this. One of the things that we do is we characterize it chemically. We use something called gas chromatograph mass spectrometry. And that allows us then to speciate very, very accurately all the different chemicals that are present, absorbed onto the surface of the soot. And we can, based on literature then, we can understand how toxic the soot is going to be when it enters our bloodstream. And then the other thing we can do, and I'm sorry I don't have a photo of this because it's quite gory, but the other thing that we can do is working with our toxicologist colleagues is that we can grow up Petri dishes of human airway cells, so living human cells taken from different donors and grown up to the point where then they're exposed to this soot. And this soot then provokes a reaction, and we can correlate then different fuels, these are different blends of biodiesel, with different levels of reaction. And this is still very much a work in progress. It's still something we spend a lot of time working on. But what we could see is that when the indicated toxicity of these soot particles was increasing because of the kinds of PAH that was present, at the same time, the toxic response from these human airway cells was also increasing. So in these two very different ways of looking at the problem, we were seeing the same response. In this case, where we were using more and more of these biodiesels, it was provoking a greater toxic response. So that's something that when we balance, when we think about sustainable fuels in terms of the impact they have on decarbonization, but also on air quality and public health, that's something we need to look at. Yes, a quick question. Okay, good question, a side question on algae. So why does this algae now look brighter than it did a little while ago? And this will reveal a shocking secret to you all. Any guesses? Yes?
Is it because, like, there's something in it that makes it dark, but it's very heavy, so it's falling to the bottom?
That is an excellent answer. So the algal cells that are inside this bottle, and which made it bright, have started sinking to the bottom. And that's because they're really heavy. And that's because this is, I'm afraid, some very dead algae that I prepared earlier and is no longer living, I'm afraid. But good question, guys. So we are nearly at the end of tonight's lecture, and the world keeps changing, and And I know I mentioned the Paris Agreement earlier and the desire to keep temperatures below 1.5 degrees C. That's not happening. It's not happened. 2024 was the hottest year on record, and it looks like that threshold has been breached, and we're seeing more and more of the consequences around the world, in Valencia, in LA, and it's not good. But there are things we can do as engineers. And I was telling you earlier about my biggest engine, our biggest engine, and that's this. This is a heavy-duty diesel engine. It's down now in that lab, my favorite lab, BA1. And what's exciting about this is representative then of those different transport sectors, things like marine, things like the NRMM. Who knows what an NRMM is? Anybody? No? It's non-road mobile machinery, of course. And so it's much bigger. It operates more slowly. These get even bigger when we start to think about those huge vessels, those great big container ships that work all across the world. And what that does is it means there's more space, there's more time for these combustion reactions to happen. And this is some very complicated chemistry that I'm not going to get into. This is a reaction called Michael acceptors, and it's not of my design. It's from Dr. Tim Dehan, who isn't here tonight, but came up with this hypothesis. And again, it's the idea of making a single change to the fuel molecular structure is enough then to completely change the reactivity. And so when we think about the whole fuel life cycle and the kind of investment and energy and resources that goes into making the fuel, perhaps providing a way for us to engineer out some of that need to invest more energy. And again, it works. And so we can see where that particular feature was integrated into the fuel molecular structure. It very much changed the heat release, and it made it more like the diesel we're trying to displace in the case of these molecules. So, thank you, everybody. It's been really great. I feel like I'm running out of time. So, I just want to thank everybody. So, thank you, everybody who came here tonight. Thank you to all the everybody who I've worked with, obviously, academic and industry colleagues. Thank you to everybody in UCL Mechanical Engineering, so all the technicians and the workshop. Thank you to all my professional services colleagues. Thank you to my family and friends who've made it all here tonight especially. And a special thanks to everybody who has spent countless hours with me downstairs in that lovely windowless basement of our lab and kept the faith. And, you know, believe me when I said things would work. So thank you, as too many of you all to name, but I will say a very special thank you to my PhD supervisor and still one of my closest colleagues, Professor Nikos Ladamatos, who I believe is watching online. So thank you, everybody, and that's it. Thank you.
Thank you, everybody. I hope this hour has been worth it for you. It certainly has for myself. I know it has gone on a little bit, but I'm more than happy to allow one or two quick questions. You know, if there are any, if Paul has not asked you enough questions, if you have any questions in the audience, there, go for it.
Going back to your ammonia procedure, my understanding is to create ammonia requires a lot of energy, high pressure, high temperature. So I wondered if there is a sustainable way to do that. And related to this, you'll do synthetic fuels using these hydrogen reactors. What is the connection between what you're doing and the concept of green hydrogen?
Thank you. So that's a really good question. So I think both of your questions actually kind of go to the same point, which is actually it's great for us to think about something like ammonia as a hydrogen vector, as a way of conveying hydrogen into a combustion system. But if that hydrogen that we're using is not renewably produced hydrogen, then those advantages are lost. And I think that's a really important point. And we didn't get into it tonight because thinking about that whole kind of life cycle of where the hydrogen comes from is huge and it's really important. And the problem we have at the moment, and my statistic might be a bit out of date, but something like 95% of the world's hydrogen at the moment comes from natural gas. And so that's not helpful. That's not a good thing because that's still releasing CO2. So yeah, you're absolutely right. There's a lot of need to investigate renewable ways of making that ammonia, of increasing the amount of renewable hydrogen we have as well to help decarbonize the whole system, really. Yeah, that's a really good point. Thanks.
Great. Any other thoughts? Yeah, go ahead. That will be the last one, and then we'll wrap up.
Thank you, Paul. Brilliant lecture. Just a very quick one. You mentioned peak oil is no longer a motivator. So why is that? I mean, have we actually found tons of new sources of oil, or is it more that now we have heavy crudes or something else? And why would you say it's no longer an issue?
I think, yeah, no, that's a really good question. So why are we not talking about peak oil anymore? And the idealist in me would like to say it's because we've realized that we can't use it, that we have to leave it in the ground. But I don't think that's the truth. Sadly, I think the reason we don't talk about it is there has been lots and lots of oil discovery, lots and lots of these unconventional sources of oil, sort of a shale, the tar sands oil, the oil that's accessed by things like fracking. So that's why it's gone away, because actually there's been a lot more oil. But I would prefer if it was because we'd realized that responsibly we can't use it. Yeah, a really good point. Yeah.
Yes, sure. Go for it. I'll excuse my own exception. Go for it.
I was wondering how you can justify the amount of the money you are going to spend for post-processing for any type of biofuel you're going to process, you're going to produce. For example, we know that we use corn, soya beans to create that, but the process is very expensive. And purifying that and also get rid of the wet sometimes. So how you can justify this in this condition?
Yeah, that's another really good point. So how can we justify that investment of money, but also I think energy and resources when it comes to upgrading into making some kind of sustainable feedstock into a fuel? And I think the answer is it's really hard to. And so we need to minimize the amount of energy that goes in. And so that's kind of one of the points I wanted to make, is that when we think about future fuels, they don't have to resemble the kinds of fuels we've been using before. Perhaps they can still contain some oxygen, for example. Perhaps, especially as we move to larger engines that are more tolerant of fuels that are further away from the conventional specification, we can find a kind of a compromise point where actually we have a fuel which is less refined, has had less of that investment upstream. Because yeah, I agree, we have to do as much as we can to reduce that investment. Not so much the economics, even though I know that's important to make it happen, but more so the resources and the energy that goes in.
Wonderful. Okay. Thank you very much, Paul, for amazing lecture. Great. This was brilliant. So I learned a lot. I'm sure the audience learned a lot, and we had very active and participatory audience here. So I think we should acknowledge that. And I think it's fair to say that all of you, including Paul, have more than earned the drinks and nibbles that we have waiting for you downstairs. I think we can go from both the doors. Just make yourself one floor down, and I think you will see. Or just follow along one of us. We should be okay. Thank you, Paul.
Okay, thanks,
Amazing.
Manish. Thanks again, everybody. Thank you.
What an amazing